Okay, so I'm going to start. We're going to kind of take apart. This is one of my favorite things to talk about. We're getting into the fundamental theorem of Galois theory. But before I state it, I think this example that I'm going to give you illustrates a lot of good stuff and will be very good. What I want to do is I want to consider my base field to be rational numbers. Right. Example. Let's consider my base field rational numbers, and alpha is cube root of 2. This is the real root of polynomial x cubed minus 2. That is an irreducible polynomial by Eisenstein of the rationalist. And I think we can all agree that cube root of 2 is the real root. It's got 2 other roots though, right? And they are complex conjugates of each other. And actually, to get those roots, I'm going to need this guy. I'm going to let omega be -1 plus radical -3 over 2. This is the primitive cube root of omega. Some of you, if you're like kind of complex, plain kind of junky, it's e to the I 2 power 3. And actually you can do the, so that's going to be like cosine of 2 power 3, which is minus half, plus I sine 2 power 3, which is this bit right here. Notice that omega is a root of x cubed minus 1. Polynomial, however, isn't irreducible. More precisely, omega is a root of x squared plus x plus 1. So I'm going to make some observations about omega that might be useful to me in a bit. Notice that omega squared plus omega plus 1 equals 0. So this means that omega squared is minus omega minus 1. And this is also omega bar, right? Because the square of this is e to the I 4 power 3, which is actually the complex conjugate of this thing. So, which is also omega inverse. Right. So, yeah, so that appears as 3 things. So omega squared is the same thing as the complex conjugate of omega, which is the same thing as the inverse of omega. Yes.
Oh yeah, I was just about to ask.
Right. Now, what I want to do, and this, I think, like I said, I think this really kind of illustrates what's going on with Galois theory. The roots of are cube root of 2, which is alpha omega, and alpha omega bar, which is alpha omega squared, which is alpha omega n. Those are the 3 complex roots of that irreducible polynomial. Okay. Now, what I want to do is I want to consider, we're going to talk about this later, this is called the splitting field of this polynomial. I'm going to build this field. This is the smallest field containing Q and all the roots of this. I'm going to call this F. Now, of course, if I want to have a root, if I want to have all the roots of this polynomial in my field, for sure I'm going to have to get this root because it's one of them, right? And actually, if I go ahead and stick on omega 2, I get all the roots, right? And notice, by the way, that any field containing all three of these roots of this polynomial has to contain alpha and alpha omega. So it has to contain this divided by this, right? So it has to contain omega anyway, for sure. Everybody agree with it? Now, let me make some observations here. What's the degree of this extension here? This one should be, what'd you say it was?
I said one, but I meant two.
How about three, sir?
Fair point.
Because that's the root of an irreducible cubic. How about this extension here? Well, you need to ask yourself, what's the irreducible for omega? This one right here is quadratic, right? Now, it doesn't do Eisenstein very easily, but it is degree 2, right? So one of two things happens. This is either irreducible or it breaks down into two linears. And if that were the case, then this root omega would have to be in the rationals, which is, of course, ridiculous. So this has to be 2. How about this? I think this falls from the homework problem, actually. This is 6, and I know that for sure because 2 and 3 are relatively prime. I think this is the homework problem. This is actually an extension of degree 3, and this is 2. But because it's 2 and 3, the what do I call it? The composite of these two, which is this, must be of degree 2 times 3, which is 6. That means that this is a 6-dimensional vector space over Q. I'm going to go ahead and give you a basis. There are many bases, as you might expect. This is a linear algebra thing. I'm going to pick one that I think is good for this problem. So a basis, one of many, consists of 1 alpha squared omega alpha squared. I'm going to use this one. There are other bases, but I think this helps. This is one of the best to illustrate it. What I am going to do is I am going to make a table of all the automorphisms of this field here. All of them. And let me point out that any automorphism, if I know what it does to the basis, I know what it does everywhere, right? Because the automorphism itself is a linear transformation of the Q vector space, right? And so it has to be Q linear. So if I know what it does to the basis elements, I know everything. And I'll go you one step further. If I know what this thing does to alpha and omega, I know everything. Because this is more than a basis, because it's also sort of closed under multiplication. So if I know the automorphism takes alpha to Fred, I know it takes alpha squared to Fred squared, right? And so forth, right? So let me make my table here. It's 1 alpha squared, omega alpha, omega. Actually, I should spread this one. And you guys can help me fill in the table here. 1 alpha squared, omega alpha squared. And I am going to give these all suggestive names. Sounds like I'm doing something right. And they're going to sort of suggest the action on the roots. So I'm going to call this, one ID. And like I said, to understand what happens here, really all I need to know is what happens to alpha and omega, and I can kind of fill everything else in. Now, do y'all remember, I know it was a long time ago, but whenever I have an automorphism of this field, what does it do to these three roots? Alpha, alpha, omega, and alpha, omega squared.
It's something to another root.
That's right, it has to permute them in some fashion, right? So any automorphism, and by the way, if I know that permutation, right? If I know that alpha goes to alpha, and alpha omega goes to alpha omega, and alpha omega squared goes to itself, I know it's the identity, right? On the other hand, if I know that alpha goes to this one, and this one goes to this one, then I can deduce it, right? So to me, that says, you know what? How many permutations of those three roots are there? At most. There's 6 permutations of them. Do they all correspond to an automorphism? Well, let's find out. One automorphism, let me get this mess out of the way. It's the identity, of course. I am going to do some other ones. And I'm going to tell you what these do. We'll kind of work backwards. B, 2, 3. B, 1, 2, 3. B, 1, 2. Okay, so let me kind of record what I want these animals to do. And like I said, I want to focus on what happens this here. This is the identity. So yeah, I know what the identity is here. I'm gonna, and of course, by the way, I also know that for sure, right? Because all these automorphisms have to fix Q. Now for 1, 2, I'm going to take alpha to omega alpha, and omega well, by the way, let me ask you this. Hazel, you pointed out that I permute these, right? So alpha has to, no matter what in my table, alpha either has to go to itself, this or this, right? In my table. Where can omega go? Well, look at omega's minimal polynomial. It's this guy. Agreed? Omega is one root of this. What's the other root? Yeah, the other one's omega squared or omega bar or whatever. Yeah, actually, omega bar is probably the most obvious one, right? Because we all know the old chestnut about, you know, the roots come in complex conjugate pairs, right? But yeah, so since omega bar is omega squared, I'm going to send omega to omega squared, or it's conjugate, if you will. Let's see what happens here. What happens to alpha squared? Well, alpha went to omega alpha, so this goes to omega squared alpha squared. Everybody agree with that? And everything else I can kind of piece together. Omega goes to omega squared, and alpha goes to omega alpha. So where does omega alpha go? Omega cubed alpha, and omega cubed is 1. So this just goes to alpha, right? Omega goes to omega squared, and alpha squared goes to omega squared alpha squared. So this goes to omega 4 alpha squared. So this is omega alpha squared. Everybody okay with that? Notice that this is why I call it phi of 1, 2. If I order this number, notice what happens is this takes alpha to alpha omega. Everybody agree with that? And it takes alpha omega to alpha. So it swaps these two. Now, alpha omega squared is not in the table. But we should be able to figure out that it goes to itself, because omega squared, well, if omega goes to omega squared, then omega squared goes to omega, right? And so that means this goes to omega and this goes to omega alpha, so it goes to alpha omega squared again. So it fixes that, and that's why I call this what I did. Yes.
How do you know how many times to multiply by omega? Cause like,
And where's the confusion?
or like, cause I know it's like omega alpha and then it's omega squared. And then there's two alphas, so I was just assuming like you square omega because it's alpha, like is it by the power of alpha?
So the way I got this is I know where omega goes and I know where alpha squared goes, right?
Mhm.
So where does this go? I'm using the homomorphism property. This goes to omega squared and this goes to omega squared alpha squared. So it goes to omega 4
Okay.
alpha squared, but omega keeps the identity, so I simplified this now. Everybody okay with that? Okay, for B13, what am I gonna do? I'm gonna go to omega squared alpha and omega squared again. So I'm sending omega the same place here, but I'm sending alpha this time to the third root, right? Hence the 1, 3.
Dr. Clinton,
Yes,
our basis doesn't have all of the, like, it doesn't include omega squared alpha. So, like, are we just assuming that, like, when we end up with the new, every column, are we just assuming that it's a basis? We can show it.
oh, it is a basis, you can
Right.
show that. And in fact, I think it actually follows from the proof I gave you, the multiplicative part of the, but you can figure out, even though omega squared alpha is part of our basis, you can still figure out what happens to it. Because if you look at phi 1,2 of omega squared alpha, this is phi 1,2 of omega squared, phi 1,2 of alpha, correct?
Mhm.
And now just look at the table. Well, okay. So in this table, since omega goes to omega squared, and that's the other root has to go back to this. If you don't believe that, this is phi 1,2 omega squared, phi 1,2 alpha. So this is omega squared squared. Phi 1,2 alpha is omega alpha. So this is omega 5 alpha, which is omega squared alpha. So this left omega squared alpha alone.
Or could you use that identity where you have omega squared is equal to negative omega minus?
Sure, yeah, I'm quite sure of it. So how does this table finish off? Well, we square alpha. I'm sorry, alpha goes to this. When we square that, that's omega 4, which is just omega alpha squared. Let's see, how about omega alpha? It should be this times this, which is omega alpha. And this last one should be where this goes to where this goes. That should be alpha squared. Everybody okay with that? And again, what's the second root? So this takes the first root, alpha, to the third root, omega squared alpha. You can check this goes back, and also kind of as a gut check, omega alpha goes to itself. Right, so the second, the one I remembered second is fixed here. Right, okay with that? And as you might guess, this is phi of 2, 3. If you follow my pattern, that probably means I'm going to leave alpha alone. Right? And I better not leave omega alone because I've already done that. That's the identity. So this better go to omega squared. And so let me finish this one off. I can finish this one off. This is just the square of this. This is just omega squared alpha. And this is just omega squared alpha squared. And there is a friendly, old-fashioned name for phi of 2, 3. Anybody know what the name is? This one right here is complex conjugation. Right, because it fixes the real stuff and it conjugates the other, right? And notice this makes sense because what does this do? What does this automorphism do? It takes the two complex conjugate roots and swaps, leaves the real one alone. And so this one actually is complex conjugation. Right, okay with it. Okay. Now let's see if we can send these on a bigger dance. For the next one, I'm going to go to omega alpha and omega. So basically, I'm going through all the possibilities. I went omega alpha and omega squared. What happens in this one? Well, in this one, alpha squared better go to omega squared alpha squared. And let's see here. Omega alpha should go to omega squared alpha. And omega alpha squared should go to alpha squared. Now, what happens in this one is, actually, I do have a little bit of room here on the rights. I think I can put something here. Notice for this one right here, what happens is alpha goes to omega alpha, and omega alpha goes to omega squared alpha. And you can check that this goes back here. I'll do that. 1, 2, 3, omega squared alpha is phi of 1, 2, 3 omega squared, phi of 1, 2, 3 alpha. And phi of 1, 2, 3 omega is that. So then I'm sorry, of omega. Should write better, shouldn't I? Phi of 1, 2, 3 omega is omega, so that'd be squared. And phi of 1, 2, 3 alpha is omega alpha, which is alpha, which is where we said it should go. So this induces the cycle 1, 2, 3 on the roots. And finally, this better be what's left over. So this has to be omega squared alpha and omega. And what this is going to give you is the square of this is going to be omega alpha squared. Then omega alpha, that's alpha, and omega squared alpha squared. Okay, any questions on that?
So did you choose where alpha and omega were and then?
That's right, that's
Okay.
right. Well, actually, to tell you the truth, believe it or not, I played around with other iterations of this. It's actually harder to do a basis with, in fact, you might say, well, Jim, why didn't you just use a basis that had all three roots in it? Alpha, alpha, omega, and alpha, omega squared. There's a reason I didn't do that. Can anybody tell me what it is?
And not linearly independent.
They are not linearly independent because the sum of those three roots is actually actually it should be one of the coefficients here. It's actually in this case 0, right? Which is the x squared term here. And so this was sort of the best basis I could come up with, where I've got 2 out of the 3 roots in it, and then we can figure out what happens to the third, right? So that was a problem that I faced. But see, notice every automorphism induces a permutation of the roots. And once I tell those roots where to go, that gives commands there. If I tell all three of these out, in fact, I only need to tell two of them where to go, and that's enough. In fact, once I tell two of them where to go, it tells me where the third one has to go. But if I tell these three roots where to go, that determines the automorphism. Now, this irreducible polynomial, x cubed minus 2 had three roots. I've sort of slugged through all the possibilities, right? And all these, in fact, are automorphisms. It's actually these are all automorphisms, and they exhaust my possibilities. So in this case, for this particular example, the Galois group of well, I'm gonna let that is isomorphic test.
So is it closed under addition no longer? Or is it closed?
No, the Galois group is the Galois group only has the one group operation, and it is function composition of the automorphisms. Everybody get where I got this table. I mean, good Lord, nobody wants to do this like a 10th degree polynomial. But there's a great theory behind it. So let me illustrate something. Look at this field here. That is a 6th degree extension of Q. Can somebody give me all the intermediate fields? How many of them are there? Are there only finitely many? This question, I don't know about you all, but I don't think that this is quite so clear, because this is certainly an infinite field. It is a modest 6th degree extension, but how do you even know that there's only finitely many fields between here and here? I mean, I've listed a couple, right? Are there more than these two? And the answer is yes, there are more. In fact, let me draw another picture that goes along with this table and better illustrates what's coming on. And this is kind of the heart of Galois theory right here.
Dr. Cody,
Mhm.
there's more even up to isomorphism.
Actually, there's only finitely many, but there's more. Yes. So what did I have up there? Cube root of 2.
And omega.
Well, technically, yes, but actually, the only proper intermediate ones, they're all one of those two up to isomorphism.
Okay.
Let me start with this. Let me give you a problem that you might think is easier, because on the surface of it, it certainly is. This problem, I hope we can all agree, is a much more sane problem, because S3 is a group with 6 elements. I mean, there's only finitely many subsets, and very few of those are actually subgroups. So I know for sure there's only finitely many subgroups of S3, right? And in fact, I can list them all out in a nice little kind of lattice structure. And where do I want to start? I want to start here. There's the daddy Mike, and then there's A3. Well, actually, you know what? Forget that. Yes, it's isomorphic A3, but I want to write this out explicitly. E 1, 2, 3, 1, 3, 2. So S3 has this unique subgroup of order 3, right? That's normal. And then it has 3 subgroups of order 2. And then, of course, there's the identity. Notice that the index here, this is an order 3 group, 2, 2, 2. The indices here are 3, 3, 3. And the index here is 2. And this one is special because it's the only non-trivial normal subgroup. That's right. Now, so I'm going to draw a corresponding lattice here of the fixed fields. I haven't formally defined that yet, but what I mean by a fixed field, the subgroup of polymorphisms, is I mean everything in the field that's fixed by everything in that group of polymorphisms, right? So, what is the subfield of Q root of 2 omega that is fixed by every one of these automorphisms in the table? Well, alpha is moved by something, omega is moved by something. So actually the only thing in this example that's fixed by everything is Q. Right? And you know what? I know what the bottom is. I know what's corresponding to the identity. What in that field is fixed by the identity? The whole freaking thing, right? So I'm digging on that. Even my Tennessean intellect can get that one. So how about this? Maybe it's best to kind of wrap our heads around this and see if we can get kind of a good guess as to what this. What is fixed by the identity, which I don't count because everything's fixed by the identity. What's the subfield that's fixed by this?
Q is joined omega.
That's what it looks like to me, right? I mean, that's a good guess, right? Because every other basis element, alpha is moved actually by both of these. Alpha squared is moved by both of these and these other ones, but actually it looks to me, my best guess is the correspondence here is Q omega for this one. And notice the index here is 2, because this is a quadratic extension. This is a root of x squared plus x plus 1. And the index here is 3, and that follows from that homework problem in our earlier discussion. Agree? How about, let's look at phi 1, 2. What seems to be the fixed field of phi 1, 2? Good gravy. Nothing on that table looks like it's fixed, right?
Omega,
What is it?
omega squared alpha.
That is correct. If you remember, this thing permuted the roots 1 and 2, but it left the omega squared alpha alone. By the same kind of token, if you look at 1, 3, this is a little bit more obvious. What's fixed by this? It looks like omega alpha. And what's fixed by 2, 3? The complex conjugation. Well, the complex conjugation is a little bit more lucid, perhaps. That's just the real root. Notice again, all of these are the 3 distinct roots of the irreducible polynomial over Q, x cubed minus 2. So these are all of degree 3. And again, by earlier discussions, these are all 2s. Everybody, yes.
How do we get the Q omega squared alpha?
Well, because I know that omega squared alpha is actually fixed by phi of 1, 2. We did that computation already because we did phi of this and we got phi 1, 2 of this was just this again. And so this, I'm not being very precise. This is not a hardcore proof. This is kind of my intuitive. This is what looks like it's going on. We're going to build this up in a bit, but everybody kind of see what's going on here. And this actually, this is the crux of Galois theory, and we're going to discover that this is true, is if you have what we call a Galois extension, which I haven't formally defined, but I will in a moment. If you have a Galois extension, then there's a one-to-one correspondence between the Galois group of the big guy over the base field and intermediate fields. And the indices of the subgroups correspond to the degrees of the extension. And what's more, by the way, this was a special subgroup because it was normal. These other two were kind of crappy because they're not normal. This field extension is special as well. Anybody know why?
Unique.
What's that name?
It's unique. Exclamation.
Oh, well, right. I mean, in this particular case, that comes out as a corollary. But if you notice, if you remember, this is one of the last examples we did before spring break. Do you remember how Q adjoined with the cube root of 2? The Galois group of Q adjoined with the cube root of 2 over Q was the identity, right? Because any automorphism of just Q alpha has to take it to another root of x cubed minus 2. So it would have to either take it to itself or one of these two. But these two are not even real, so it doesn't stay in the field, right? And so the Galois group of this over this is 1. This means this extension, this one over this, is not Galois. And the problem is these subgroups are not normal here. This extension from here to here, this is a degree 2 extension in this Galois. So that's going to be, you can also pick out by the normality of the subgroups some of the nice properties of the field. So that's kind of it in a bit of a nutshell. Are there any questions over the exam? This is just basically kind of painting a beginning sort of intuitive picture, if you will. Any questions?
Dr. Clark?
Yes.
You were saying that like the heart of Galois theory, like you were saying something about like a one-to-one correspondence, right? So if you loosen some of the restrictions, do you lose like the one-to-one? Like does it become onto a one-to-one?
It depends on what restrictions you lose.
Okay.
And what we're going to focus on is there are bigger, I mean, Galois theory is more encompassing, but we're going to focus on just finite extensions of not just rationals, but that's where we're going to start off anyway. So let me give you some of this background on it first. Let me give you kind of warm up theorem, which is also kind of a definition of theorem 14.2.4. Okay, so this is kind of a general statement that I need. This kind of is helping me take care of that business over here where I talked about fixed fields and correspondence. Here I'm going to make this more precise. Let K and E and F be fields. And I think H, a subgroup of the Galois group of F over K. Don't let this intimidate you. The Galois group of F over K. These are just the automorphisms that fix K. That's it. They leave K alone, they're an automorphism of F. These are all the automorphisms. H is perhaps some subgroup. Let H prime. Okay, so H is group. H prime is actually a field. And what field is it? It's all the crap in F. Such that sigma V is equal to V for all sigma in H. This is called the fixed field of H. Field extension. That is to say, H prime sits somewhere between K and F. This is called the fixed field. And there's a corresponding one for an intermediate field. So, given a group, I can make a intermediate field to the extension, and given an intermediate field E, E prime this is a subgroup of the Galois group, and it is all the sigma in the Galois group such that sigma E is equal to E, all E. So it's everything in the Galois group that fixes everything in E. Let's at least kind of outline what this is. So I need to show that H prime is an intermediate field extension. Well, let me first settle something. Certainly, certainly as such, this is true. Yes,
What, like, we defined E prime, what's the statement we're making about E prime? That it's a,
oh, I'm sorry. Is a subgroup of the Galois. Or F, okay. Wouldn't surprise me. Oh, no. Certainly, H prime is between their sets. And here's why. Notice that everything in the Galois group fixes everything in K, right? By definition. So certainly K is contained in H prime because this is an automatic. And by definition, this is contained in F, right? So as sets, I've got no problem. So really, all I need to do is show that this is closed under addition, subtraction, multiplication, etc. So notice that let's say U and V are in H prime. This implies sigma U and sigma V, sigma U equals U, and sigma V equals V. Therefore, sigma UV is sigma U, sigma V, which is UV. Sigma U plus V is sigma U, actually I'll say plus or minus and sigma u over v is sigma u over sigma v, which is u over v, if v is not zero, of course. Right, so H prime is a field. No problem there. And it's similar for, similar for the E prime. So notice that the identity function on F is an element of E prime. So E prime is not the empty set. Because certainly the identity function fixes everything in A, in fact, it fixes everything in F. So in particular, this is not the empty set, so I can use subgroup criteria. So let sigma 1 and sigma 2 be in E prime. And suppose E is in E. Notice that sigma 2, well, notice that sigma I of E equals E. And since sigma 2 of E equals E, this implies E equals sigma 2 inverse of E. Because again, it's an automorphism. Therefore, sigma 1, sigma 2 inverse of E is sigma 1, sigma 2 inverse of E. By the above, this is E. And by assumption, this is E. Therefore, sigma 1, sigma 2 inverse is in E prime. And so E prime is a subgroup of the Galois group. Okay. Let me remark that notice that look at 1 prime. Okay, so 1 is the subgroup, it's the identity subgroup of the Galois group. 1 prime is everything in F such that sigma V equals V for all sigma in H. Well, this is only the identity. This applies to everything in F. So 1 prime is all of F. On the other hand, but if G is the Galois group of F over K, it is not always the case that G prime is K. Well, remember what you, oh yeah, I did, right. Yeah, so the other extreme doesn't go the other way because, well, actually, before I pull back the curtain, can anybody give me an example where this doesn't hold? So if you look at, so this is again a rip off of that example I gave you guys right before spring break. If you let K equal Q and F equal Q root 2, then the Galois group of F over Q is the identity. Right, because the only automorphism of this fixing this is just the identity automorphism. And notice in this case, G prime, which equals 1 prime, is all of F, which is not equal to K. And that distinction will define what we call Galois groups. Yes,
What
or
is,
Galois extensions, my bad.
what is 1 prime and G prime?
This definition,
Oh, okay.
right. Other questions? All right. Well, you all have a good one, and we will see you by Wednesday.